Welcome to Surge. I'm Aaron Newman. I'm the director of Surge, and I just want to draw your attention right away to Jordan, who you've probably interacted with already, who's our program coordinator and go-to person for everything. So welcome. This is fantastic turnout. Happy to see you here for our Neuro-Hackathon. And I'm going to talk for a little while, just a little bit of background. Some of you are probably sick of, I recognize you from like every class I've talked in, I think. So you're probably sick of hearing this spiel, but I'm going to talk a bit about Surge, what we are, and so on, and then go into kind of a very brief crash course on what is EEG. How many people are familiar with EEG already? I'm curious. Okay, pretty good, awesome, okay. And so I'll give you just sort of a bit of context and background, and then Colin Conrad, who's over here, who's one of our mentors, and I are going to sort of go a little deeper into what BCIs are, brain-computer interfaces, and how that all works. All right. So Surge is a sandbox that's funded by the Nova Scotia government, and it's one of 10 sandboxes across the province. So we have 5 at Dal. So we're the science one at Surge. We also have ShiftKey, which is computer science, Cultivate for agriculture, IDEA for engineering, and a health sandbox that's still sort of in the works. And then there's sandboxes at every university across the province, and NSCC as well. And so it's a network, and the idea is to build on what's normally taught in universities or historically taught in universities with design thinking and innovation and kind of what you might call 21st century skills. So things that are really focused on, rather than just following the recipe or like, here's the problem, here's the right answer, how do you get from A to B? How do you go out and find real problems and address real big problems and turn them into like bite-sized pieces, brainstorm different ideas for solutions, assess the viability of those solutions in terms of how well they actually meet human needs, how technically feasible they are, how economically feasible they are. Can you wrap like a business model around it that makes it work, whether that's for profit or not for profit, but thinking, sort of putting science in the context of that bigger picture. So that's what Surge is all about. So we have this space, which we use as a classroom space for all our events, also can serve as like a maker space and incubator for startups. We actually have workshop facilities back there as well. And we're doing programming like this. So this is what we call non-curricular programming. You don't get academic credit. There's no grades on the line. You're just here to learn and have fun. And that's a lot of what we're trying to do, is provide different kinds of learning opportunities from traditional credit, for credit kind of class stuff. And we're also serving as a startup incubator. So coming online this summer, we're going to be doing our residency program where early stage, not even startup, but pre-startup teams who are interested in exploring an idea around a startup can come and get some mentorship and a bit of financial support for like prototyping or just kind of kicking the tires and figuring out if they have something that they could carry forward as a startup. So we're working on, I sort of already alluded to this, helping teach things like problem definitions. So how do you actually figure out what important needs are that people have? Often, especially coming from science, people are really, in love with a particular technology or an idea, and they want to find an application for it. But the better way to do things is to find real needs and figure out how you're going to address needs that lots of people have or people find very important, and build solutions around those using the most appropriate kinds of technology. So trying to reframe that and teach you those skills. How do you find solutions that work in terms of real human needs? Technical understanding, so understanding like intellectual property and how do you assess whether a technology is actually ready for the real world in terms of reliability, safety, quality control, all that kind of stuff. What we call soft skills, which are really valued by employers these days, is how well do you work in a team with people from different disciplines. So in this room right now, we've got probably lots of different disciplines. How many psychology people? A few. How many neuroscience people? A few. How many computer science people? Engineering? Not otherwise accounted for? What are you? Sorry? Cool. All right. So yeah, so broadly cross-cutting, right? So you're going to be working with people who have different backgrounds, different knowledge, different assumptions even. So how do you work in those kinds of teams? How do you become a lifelong learner? Professionalism, networking, standing up in front of people and pitching an idea, where you realize that they don't necessarily have the same technical understanding you have, all this kind of stuff, and a basic understanding of how businesses work and why they exist and how they operate. Because ultimately, most of you are probably going to be working at some point in your life in a business, for a business, or running a business. So it's important to understand science in the context of the organizations that actually can bring scientific discoveries and applications to fruition, which is a business. So we've got our Discover program that we're rolling out next year, which is a weekly series of 1-hour workshops on different topics. So you can just come and pick and choose sort of thing. Deep dives, which are events like this weekend, hackathon event. So this is our Neuro-Hackathon. We did a synthetic biology hackathon last weekend. Later in April, we're doing a Launch Oceans startup weekend around ocean technology and oceans-related startups, aquaculture, ocean tech, sensing, all kinds of stuff. So broad, like we're trying to touch on different areas of science with these deep dives and really get your hands dirty and play around with something. And then we have a class, I'll talk more about that in a minute, and the residency program is the incubator that I talked about. And the whole idea is to both give you this flavor of different things that are available to you and different skills that might help you as you sort of move on from your degrees. But also, there's a huge and growing startup ecosystem in Halifax. Around the world, entrepreneurship and startups are becoming more fashionable and more, I think people are realizing that it becomes a mechanism to sort of test out different ideas in a much more agile way than a big company, which might be very conservative about the kinds of innovations or things it does. But within the Halifax community, there's a huge amount of available support, mentorship, money, different kinds of organizations to help startups, sort of start up. And so the idea of Surge is to do the training, but also prepare people to apply to things like Collide, Launchdale, Idea Hub, Creative Destruction Lab, Volta, all these different organizations that are out there to sort of take companies from where we bring them to the next stage where they're actually ready to grow and really mature. So this class we're rolling out, we're doing a pilot this year, which is running half a year. Next year it's a full year capstone class for fourth year students. It's an SCIE code, so regardless of your major, basically you can take it. And the idea is to bring in a class size is 50 students, so reasonably large. It's the size of this room, basically. Bring in students from across different disciplines in science to work on a full year experiential learning project where each team basically identifies a problem that they want to address and works to first really define that problem. And a lot of what we push all the way through the course is what we call customer discovery, which means you go out and you talk to people who you think are potential customers or people who have the need that you're trying to address, and really try to test your assumptions about what they need against what they actually need and what they tell you they need, and try and find that fit. So defining the problem and the need very clearly, and then starting to develop different ideas for solutions, and again, going out and testing how those solutions play against the people who are your potential customers. And by customers, I mean users, right? So it could be, you could again be doing a not-for-profit where you're not necessarily taking money from people, but figuring out all of those different pieces, and then take it through how do you build a business model around that. So how do you figure out, okay, we've got this possible solution, sounds great, we'd love to do it, how are we going to pay for it? How are we going to pay for the research and development to get it to the point where we can prove it works? Then how are we going to solve manufacturing, who are we going to sell it to, how are we going to sell it? All these different pieces that you have to think about. So we take you through that whole process and test hypotheses around all of these things and figure out kind of the optimal business model, as well as later in the course doing actual sort of prototyping and early stage development of the product so you can really test the feasibility out. So it's a really fun class for me to teach because it's, like I say, it's experiential, so you're not sitting there listening to lectures and taking notes. There's no exams. It's all going out, talking to people, coming back, reporting, getting feedback, getting sort of grilled on your assumptions, and a lot of sort of critical thinking skills being developed, and doing that repeatedly, as well as case studies. So reading, case studies of different businesses or ideas around startups and discussing those. So very interactive, very different probably from most of the classes you've taken. So if you're going into fourth year next year, definitely take a look at that, consider it. And if you're sort of earlier stage, think about that down the line. And then one other opportunity I want to promote is the Provincial Sandbox program is running this Creativity and Innovation Boot Camp. So they've done this for a couple of years now. It runs at Acadia University, and each sandbox sends 10 students to it. So there's going to be 100 plus undergraduates from all across the province, all different backgrounds, majors, and so on, all focused. So you're going to form into teams and address a design challenge, which is based on Canada's new food guide and the challenges that that presents. And you'll go through workshops on creativity, innovation, design thinking. It's much more focused on that early stage, defining problems and solving problems and figuring out, sort of human-centric sorts of solutions than on the entrepreneurship or business piece of it. So it's sort of that earliest stage, really prepares you for a lot of different things. The people I've talked to who have gone through it say it's fantastic, life-changing, really great for building a network of enthusiastic, like-minded people across the province. Lifelong friends. So it's at Acadia, 2 weeks. All your board is, your residence is paid, meals are paid for, and you get a $1,000 stipend to kind of offset the lost wages because you can't work during that period, obviously. So if you're interested, there's a website for that. Applications are open now. We're taking them up until March 25th. And it's like a central application website, and then you'll sort of, if you're coming through science, you indicate Surge as your sort of home sandbox, and we'll take it from there. Yeah. So anyway, you've probably already found some of the Surge programming on the web because you're here. But we have a website, Twitter, Instagram, so you can check us out. And yeah, that's Surge. So before I go into the EEG stuff, any questions about Surge and all that stuff? Yes.
Okay. Washrooms out that door before you hit the outside door, and just to the left, there's also a water fountain there. Pizza will be coming. There's coffee, and I can get a kettle for tea. If you're gonna stay for the weekend, consider bringing a reusable water bottle and potentially a reusable coffee mug too. That's all. Yeah.
All right, thanks. All right. So EEG. So EEG is basically a way of recording brain activity using electrodes placed on the head. It was discovered in the 1930s by this guy, Hans Berger, kind of accidentally. So he was in the Prussian cavalry, so he was in a battle, fell off his horse, had a concussion, recovered from it, but later when he was talking to his sister, she said, yes, at that very moment I had this premonition of danger and that you were in danger. And that convinced him that ESP was a thing. And so he set about to uncover the physical basis of ESP. He failed at that, but he discovered EEG instead. And basically just started, at this point, people knew that electricity probably had something to do with brain activity. People would record this in neurons in animals, but in the human brain, it wasn't very well understood. And he was putting electrodes on people's heads and came up with tracings like this top one here. Hello, pointer. So the top one is what he recorded from his assistant's head. And at the bottom, this, think back to 1930s, they didn't have digital computers. And so this was being traced out. You've maybe seen this in old movies, right? This thing that's tracing something out on paper as the paper's moving. But the paper didn't even move at a steady rate. And so this is actually a tuning fork that's vibrating at a set rate. And so you know just by counting peaks how much time has passed. So that's what that is. And so these are actually from his original publication, the kind of things that he observed. And we now know that what he observed is called alpha waves. So they're generated by the visual cortex when people are kind of bored or quiet or sleepy. But he wasn't actually well accepted in the scientific community because he wasn't recognized as a researcher. He was actually a medical doctor. So he had some chops, but not really well versed in neurophysiology. And so he didn't really have an explanation for this. To his credit, he didn't try and call it ESP. He'd sort of moved on from that, but he didn't get a lot of credit. And then later on, I don't have a slide, but Adrian and Matthews, who were two more well-respected, established physiology researchers, kind of replicated and extended his results. And as sort of an interesting point in sort of how science is done and that sort of thing, critically what made their work more credible, besides their sort of pedigree and their background, was that they actually came up with a model of why this would work, because people knew that neurons worked at that point by producing action potentials. So a neuron sort of fires and there's like a spike of activity and then it's quiet for a while and then a spike again. And so what people didn't understand was if neurons are working by spiking, why are we not seeing spikes, but we're seeing these sort of slowly oscillating kind of waves? And what Adrian and Matthew showed was that if you have lots of neurons that are spiking, but they're spiking at slightly different times, when you kind of average that over time, it ends up looking like these more slowly oscillating waves. And so it's not that you're recording the activity of individual neurons when you stick electrodes on the head, you're actually recording the activity of whole populations of neurons. And it's kind of the summed slow activity. So it's electrical activity, but sort of a level removed from the spiking activity of individual neurons. So this is what a modern EEG system looks like. So this is the cap, obviously. This is the person with a brain. These individual things on their head are electrodes. And the electrodes pick up the signal, run down into this device, which is called an amplifier. So basically the signals we record from your brain are on the order of microvolts. So if you think of like this is always fun, you know a 9-volt battery? Has anybody here ever licked a 9-volt battery?
Yes.
Excellent. Not many. Yeah, you guys, you got it. You haven't lived. So if you touch your tongue to the 2 terminals of a 9-volt battery, totally safe, try this at home, you'll feel like a little tingly electrical current and maybe sort of a weird taste. The point there is that that's 9 volts and that's like nothing. Like it's perfectly safe. It's kind of a weird offsetting experience, but it's not dangerous. What we're recording here is microvolts, so thousandths of a volt. So they're super tiny signals. And so the amplifier serves to boost those signals and basically make them big enough that we can record them accurately. And then that'll be run to a computer. And typically what you've got is a setup where one computer is recording your brain waves, your brain activity, and the other computer is presenting stimuli to the person whose brain activity you're recording, so you can control what they're experiencing and look at how the brain activity relates to that sort of moment-to-moment stimulation. So when you record brain activity with EEG, this is what you get. So these wavy lines here, each one is the tracing from one electrode on the head. This is from a system that has, I think, 64 electrodes in this case. The one we're working with today will, and over the weekend will have less, but that's okay. So this is the tracing from each one and the ongoing brain activity. And the vertical lines that you're seeing there are when we're presenting stimuli. So imagine you're sitting there, you've got the EEG cap on, and we're just doing something that's very simple like showing you pictures, right, say of human faces. And each time a picture comes on the screen, we send a little marker to the EEG system saying picture came on, and that's what those lines are. And so that way afterwards we can go back and look at the data time-locked to the precise time that those pictures came on. And that precise timing is really important because EEG has super good temporal resolution, meaning that, we're sampling the data from the system from your brain, typically something like 500 times a second. And the signals that we're recording change on the order of, after you see a stimulus, you'll see things as early as 50 milliseconds, so 50 thousandths of a second after the onset of the stimulus. Your brain's already making certain responses, and there's a whole series of different responses. So very high temporal resolution. But that also means you need very good synchronization between your stimulation and your recording system. Otherwise, you're not going to be able to see those things reliably. And in fact, the temporal resolution is so good that in audiology, where they're testing people's hearing, you can put electrodes on the head, present very brief click tones, and you can see a whole series of individual EEG responses on the order of like 5 millisecond increments that represent the information as it goes from your ear, and each sort of neuron that goes between your ear and your brain stem and then up into your brain. You can see the response for each of those synaptic junctions separately over the course of like 5-10 milliseconds. So that's very, very high temporal resolution. All right, so that's EEG. And then what we mostly look at, well, sometimes we look at EEG, which is like the ongoing continuous brain activity. We also look at ERP, or event-related potentials. And this is EEG where it's time-locked to those events of interest. And so what we do is we present, say, 100 faces at different times, and we take the data and then we chop it up, and we just take a little segment of data from the start of the onset of each picture for like 1 second afterwards. So we have all these little segments. So we presented 100 faces. We've got 100 segments of data, and that's your brain response to each face that you saw. And then we average them together. So we take all those 100, we average them together, and then we can see what's consistent in terms of your brain response across all of those different times that you saw a face. And what washes out is the random noise that's going on. And that's really critical because most of what you're seeing in a picture like this isn't brain activity, or at least not brain activity that we're interested in. Because the problem with EEG is that these electrodes, yes, they're picking up brain activity, but the brain is inside your skull. That's a good thing. The skull is very protective. It's there for a reason. It's also a very poor conductor of electricity. And so those electrical signals actually get really attenuated. So they're a lot weaker when we record them from the outside of your head than if we had the electrodes stuck directly onto your brain. Also a lot safer. The problem, though, is that your muscles also use electrical impulses. And so anytime you scrunch your face, scrunch your forehead, if you're trying to talk, move your head around, those are generating electrical activity as well. And that really washes out the EEG because it's much larger. As well, like if you blink or you move your eyes around, that's going to create signals as well that gets recorded by the EEG electrodes. And it turns out that your body is a very good conductor of electricity. That's why it's a bad idea to stick your finger in an electrical socket. It's a bad idea to drop the radio into the bathtub, that sort of thing, because water conducts electricity well. And so everything, even if it's occurring on your face, it's going to get picked up by those EEG electrodes. And so by recording the brain activity over lots and lots of different trials of presenting, say, a face, then we average them together. In principle, you shouldn't be contracting your muscles exactly the same way every time that picture occurs. You shouldn't be blinking at exactly the same time every time that picture occurs. And so all that stuff that's sort of random from time to time gets washed out, averaged out, and what remains consistent is what your brain is consistently doing every time it sees a picture. So that's what an ERP is. So that's what this figure is showing. This is actually 4 faces, I believe. This is where we just overlaid 42 responses to individual trials. We didn't average, we just sort of overlaid them. And you can see it's pretty noisy because there's lots of that noise going on. If we average them together, we get something that looks like a squiggly line. So fine, at least it doesn't look like that. And if we average more trials, so now this is 175, we can see that you get something that's somewhat larger. Actually, the scales changed there. I cheated. But you get a response that's a lot less noisy, and we have more confidence that those peaks that we're seeing actually correspond to peaks in brain activity as opposed to random noise, because this is 175 times we did the same thing, and that's what sort of falls out of it. And it turns out that there's this thing called signal-to-noise ratio. So signal being the brain activity, noise being all the other crap that we don't care about. The ratio of those two, it improves as you add more trials, right? Because the more sort of bits of information you have into the average, the clearer your response gets. But you get what's effectively diminishing returns. So this tapers off formally with the square root of the number of trials you have. So as you go here, this is, so what I'm showing here is the solid line in each plot is one set of trials, and the dotted line is another set. So in this case, it's just 2 random trials from this experiment. And the ideal thing, because this is always the same kind of stimulus, they should look identical if we have a reliable sample of the brain activity. So you can see that they don't, when you have one trial, when you have 2 trials in each average, it's when you start getting to 8, 16, still not really consistent, 32, okay, now we're seeing that those dotted and solid lines are pretty consistent. 64, 128, they're getting really clean, and then 256, super clean. But the punchline is that really you get a huge benefit going from one trial to say 16 or 32 trials, but you don't get that much benefit from going to 32 to 128, and definitely not to 256. But what you've done is, if each trial takes X amount of time, you've significantly extended the length of the experiment for very much diminishing returns in terms of the amount of data. And this comes up in the BCI context, as we'll get to, because it's sort of how long does it take you to really decode a brain signal and get a reliable response before you go on. All right, so that's ERPs. And another thing that's sort of important to understand is that if you do an experiment repeatedly with the same person on different days, you get pretty consistent results. So this is from an experiment, not that I did, I borrowed it from somebody else, where they were doing an experimental manipulation and they were looking for this effect. So basically the difference between two different conditions in experiment, doesn't really matter what they are. What matters is that this person came to the lab 3 different times, did the same experiment. Things don't look identical, but pretty reliably, like the shape of where these peaks are, which are peaks of brain activity, and the difference between them are pretty consistent. Whereas if you bring 5 different people into the lab and do that same experiment, their individual results look quite different from each other. So everybody's brain is different, and if you think about like pictures you've seen of the brain, it's like this very folded, convolved kind of structure, right? And what we're recording with EEG is electrical activity from big patches of the outer surface of your brain that are sort of radiating out, hitting your skull, being smeared out by your skull because it's a poor conductor of electricity, and eventually reaching these electrodes. So something that could be a relatively focal bit of activity in your brain gets smushed out into a pretty broad area of activity on the scalp. And then you've got multiple areas that are all sort of pointing in different directions, radiating out to the scalp that you're all picking up. And everybody's brain has a different pattern of folds, and it's a different size and that sort of thing. So just from person to person, you would expect that things would look different because their brains are different shapes, and maybe they, they're just generating different size responses and that sort of thing. Where this, again, relates to what we're going to be doing this weekend with BCI is that BCI is really about decoding brain activity. But we can't really build a model of what the brain activity should look like generically for one person and apply it to another person. We can build generalized models of broadly what we expect, but to get it to work well, you need to get data from that individual and figure out how their brain responds to these stimuli and differentially between different conditions or something, and use that as the basis to sort of train your decoder and make some sense of that, and then move forward. So you have typically like a training phase where you're acquiring some data, where you know what's going on and you have the person maybe doing things intentionally, and then a testing phase where you actually have them using that to control the computer interface in some other way. And you need to do that training per individual because of the variability in brain activity. This, I already sort of said it, but this is just a schematic illustration of where EEG is coming from. So these are called pyramidal neurons. They're a particular type of brain cell that occur primarily in the cerebral cortex, so the outer layer of the brain, which is where most of the sort of cognitive action that we engage in comes from. And they are arranged basically in this sort of format. So they're basically sort of aligned perpendicular to the surface of the cortex. This is a fold in the cortex here. And so when a bunch of these neurons become active and their activities sort of occurring synchronously, then there's enough sort of additivity that it radiates out through the thick skull and out to the cortex. And you can see something like these are plus signs here for positive electrical potential. They have to be bunches of neurons that are acting synchronously. What's the other side here? Oh, yeah. Because otherwise, if you imagine like some of these are on, some of these are off, they're doing different things. They're just going to cancel out sort of right next to each other, and nothing's going to be sort of add up to the point where it radiates out to the skull. So they sort of add together, and it's formally what we call an equivalent current dipole, which means we represent the activity of a whole bunch of neurons and like a whole chunk of the cerebral cortex just as one sort of unit of activity. And what this is showing is those equivalent current dipoles, so that has some orientation. So going back here, kind of like, you've probably learned about like the North Pole, the South Pole, magnets. Batteries have a positive terminal and a negative terminal. So when you have a field of activity like this, you're going to have a positive end and a negative end. And that's just sort of two sides of the same coin, depending on how those neurons are oriented and how they're activated. But that's going to radiate out, so the positive stuff is going to radiate out in one direction from that active brain area, and the negative electrical potential is going to radiate out from the other end. So it's a bit counterintuitive, because typically we sort of think positive big, negative small. Positive means more activation, negative means less activation. But in EEG, it's different. So basically, nothing means no activation, and something means activation. And every part of the brain that's active is going to sort of be radiating out positive electricity in one direction and negative in the other direction. So depending on where you have those electrodes on the skull relative to that active brain area, you might see a higher negativity or a higher positivity. And what this figure is showing is just if you imagine this dot is the dipole, so the active part of the brain, and the line is where its positive pole is pointing to. The same part of the brain being active in all three of these examples, just depending on how it's oriented, could give you like positivity at the back of the head, negativity at the front, positivity at the top, negativity underneath, or positivity at the front, negativity at the back. So that's all driven just by how that's oriented. So if you think back to like this one, where you've got this dip, this sulcus in the brain, depending on whether the activity is on this side of the sulcus or that side of the sulcus, you might see negative or positive stuff somewhere. Okay. So I sort of talked about the fact that signals are noisy. There's a lot of different sources of noise. I talked about like muscle and eye blinks and that sort of thing. As well, EEG electrodes pick up ambient electromagnetic noise from the environment. So if you're close to something like one of those electrical outlets, the EEG system is actually going to pick up a lot of what we call 60 hertz noise. And so one of the things that we always do with our EEG data is filter it, which means sort of smoothing it out. And so we remove some of that, the high frequency stuff, so the stuff that changes very quickly over time, and also some of the low frequency stuff, the stuff that changes very slowly over time. And that's really to remove some of the noise. So that's a critical step in building a BCI, is streaming the data in from the brain, but then filtering it out to remove some of those sources of noise that we know exist there. And then eye blinks and other things. So this is an example of a blink. So again, this is the ongoing EEG activity. This is a blink here. And the real thing to notice is how big that blink is compared to like the ongoing EEG activity. And it's typically like 10 or more times bigger than what's coming out of the brain. So those are really big deflections. And there's other things here. That's a blink. If you move your eyes horizontally, it's a little more subtle, but some of the electrodes might show sort of these sort of slow shifts and so on. And so we also need algorithms that can detect stuff like this. And as we're trying to decode brain activity, we don't want to like make false alarms and every time this person blinks, say, oh, that's a big brain response, and do something that they didn't intend to do. So our algorithm needs to have ways of finding those blinks, and that's already sort of built into the software. So that's relatively easy to do, but it's one of the things to be aware of. And ideally, as you're doing, if you're the subject who's trying to use the BCI, you try to control, like, don't do a lot of facial movement, don't blink, that sort of thing. All right, so I've sort of talked broadly, and we'll talk a bit more concretely about what brain-computer interfaces are. But there's a few effects that are pretty commonly used to drive these brain-computer interfaces. And ultimately, what we're trying to do is control something out there in the world with our brainwaves. So this might be a speller. So you can imagine having all the letters of the alphabet on the screen, and you say, I want to spell the word cat. So you stare at the letter C and focus all your attention on that, and the BCI will detect which letter you're paying attention to, and after a certain amount of time, it'll say, okay, they're looking at C, and then it'll draw the C on the screen for you. And then you change your attention to the letter A, and it'll take a little while to decode that you're paying attention to A. This is ideally. Sometimes it makes mistakes, but in the ideal case. So it gets C and then A, and it does it like that. So I'll talk about like what brain response is there. But that's the sort of thing where it's decoding essentially what you're attending to in the visual world. Another one is that you can imagine moving your hands, so moving your left hand versus your right hand. So we know that in the brain, the part of the brain that controls your body movements is called the motor cortex. It's two strips of your brain that sort of go down, so they're sort of in the middle, front to back, sort of up on the upper half of your head. So if we stick electrodes over those parts of the brain, we can record the activity of the motor cortex. And it turns out whether you're physically moving your hands or just imagining moving your hands, as you imagine that movement, so I imagine, and it's crossed over because a lot of your brain represents one side of your body on the other side of the brain. So if I imagine like squeezing that's my right hand, my left motor cortex is going right now. And if I imagine squeezing my left hand, my right motor cortex is going. And so I can just sit here and imagine making those movements, and my motor cortex is going to go up and down depending on which one I'm imagining moving. So we can decode that, and that's basically giving us two indicators, right? And so you can imagine like a game like Flappy Bird or some sort of driver game where you're character is moving forward the whole time, and you imagine left and right brain movements to move Flappy Bird up and down, or to move your car left and right, or somebody last year did like asteroid dodging or that sort of thing. So in the one case, like the speller case, you can imagine anything where you're basically decoding visual attention in space. You can come up with an application and use that signal. Anything where you require some sort of continuous sort of indicator where it's left, right, up, down, yes, no, whatever, you could use that motor cortex decoding, that sort of thing. So a couple of effects, brain effects that we tend to focus on. So for that speller, it's an effect called the P3. And this is a peak that occurs, it's a positive peak over the top of your head that occurs about 300 milliseconds after you see a stimulus. And it's biggest when you see a stimulus that occurs infrequently. So you're seeing lots of stimuli and it's occurring maybe like 10 or 20% of the time, and it's relevant to you in some way. So like in that speller case, what's actually going on is those letters are on the screen like I described, but they're flashing really quickly. Different letters are flashing at different times. And so you're attending to the C because you want to spell cat. And every time the C flashes, your brain's going to generate a P3 response because it's relevant to you, it's the thing you're attending to, and it's relatively infrequent because it's only flashing some of the time because all the different letters are flashing. So we use the P3 brain response as sort of an indicator of what you're attending to. So we can sort of decode your brain activity or what you're thinking about based on that. Another one that people sometimes use is the visual evoked potential. So this is anytime you see like some visual stimulus come on, you'll get a very characteristic pattern. This is actually weirdly mislabeled. Usually it's a P1, N1, P2. This is an N1, P1, N2. Check your slides before you use them, I guess is the punchline. Just imagine those labels aren't there. But basically there's a characteristic series of responses that occur when you see a visual stimulus. And you can look for those. But often what people do instead is, requires a bit of explanation when we get to get there. But basically you flicker visual stimuli on and off at a particular rate. So if you're flickering it at 8 times a second, your brain, those visual evoked potentials are going to flicker at 8 times a second. And if you flicker the stimulus at 12 times a second, your brain response is now going to go at 12 times a second. And it turns out you can actually have, like, imagine a screen. You've got 3 different circles on the screen, and one's flickering at 8, one's at 10, and one's at 12 times a second. And whichever one you pay attention to is the one that's going to show the strongest output in your brain. And so you can, again, sort of detect where somebody's paying attention just based on those flicker rates. And you can do some clever stuff. So people have done stuff like actually composing music. So they have a number of these things flickering at different rates, and each one's associated with a different musical note. And so I want to play a middle C, so I stare at the 8 hertz flicker, and then I want to play an A note, so I stare at that one, and this sort of thing. So it's like another hack, basically, because all your brain is doing is like responding, synchronizing its response with a visual stimulus, but then you assign some unique sort of value to that stimulus that triggers some arbitrary response in the computer. So the way you do that is this thing called the Fourier transform, which anybody in computer science probably already knows that. Some of you may not, but it's basically saying that, and this is a guy, Joseph Fourier, way back hundreds of years ago, figured out that any time-varying sort of wiggly line that varies over time can actually be represented by a combination of a bunch of sine waves. So sine waves being things like this, so slowly oscillating with a regular frequency, so a number of peaks per second. And so the Fourier transform is basically saying we take something like an EEG that looks like a randomly squiggly line and figure out what combination of sine waves best creates that pattern. And then we can look at that and we can map that out in what we call the frequency domain, where we plot frequency on the x-axis, power or amplitude size of the signal on the y-axis. And in this case, so frequency hertz just means cycles or peaks per second. And so if you think about what I was describing before with the flickering visual stimuli, you would see a peak in this frequency spectrum at the frequency that the thing was flickering at. So in this case, that looks like that's probably about 12 hertz. 12 cycles per second, you see a peak there. And in this case, what I've done is sort of modeled if you had multiple different signals going on at once, so different peaks. That one at 60 hertz is from the electromagnetic noise because our alternating current in North America is generated at 60 hertz. So that's an artifact. Those ones are all the brain activity. So that's one of the tricks or signal processing things that you do in BCI or can do is pass the EEG through a Fourier transform, turn it into this thing, and look specifically at how big the signal is at like 10 hertz or 30 hertz or 40 hertz or whatever. So with the flickering visual stimuli, as I said, that's one thing you can do. But even that motor cortex stuff that I talked about, and I think, is that my next? I'll get there, also relies on that. So with human EEG, we actually have Latin words that are labels for different bands of frequencies that we know relate to different things. So like delta is associated with brain activity, go back, with sort of sleep and low levels of consciousness, theta with certain types of cognitive activity and attention. Alpha, I mentioned early on, that's that Hans Berger, the first thing he discovered was alpha. So it's sort of the brain's idle mode, but also the motor cortex, that's one of the signals you get as you're imagining movements or actually executing movements, is an increase in amplitude in that 8 to 15 range, and also in the beta range, 16 to 30 hertz. And then gamma is associated with memory and some other processes in cognition. So there's different bands that have sort of different associated cognitive processes. I mentioned, so steady state evoked potentials is the fancy word for that flickering light thing that I described before. Skip over that. And then this one is just demonstrating that motor cortex activity. So this is what the EEG would look like if you were imagining moving your hand. And then that's the frequency spectrum, right? So that's the big peak that tells us, okay, that's the mu rhythm that I just mentioned. And this is a map looking down at the top of the head. Where that's biggest is over the right side of the head in this case. So the person's probably imagining moving their left hand. So we can decode that. And so BCIs are really a kind of, gross, primitive mind reading or brain reading around particular signals that we already sort of understand and can characterize quite well. We can't really imagine all or decode all the things you're thinking, but we can decode certain things like if you're imagining movements or seeing visual stimuli and things like that. Sorry, what were you asking?
Oh, the negative 500. So you're saying the person moved their left hand?
Oh, yeah. Yeah, so, and that goes back to this thing that I was saying about the dipoles, right? So you imagine that the dipoles, the little battery in your brain is oriented like this. So the positive part's pointing out that way, and then the negative part's pointing out that way. So you're always going to have the two, yeah.
So do most BCIs right now use machine learning, or do they just play with direction?
They don't necessarily use machine learning. So machine learning is one of the ways that you can figure out how to decode, because really what you want to do is decode something like, are they imagining the right hand moving or not, right? So you have to figure out some like threshold level. So, in spite of what you might have heard about, like you only use 10% of your brain or blah, 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 your brain's generating lots of activity all the time, right? So you're always going to get some level of mu rhythm coming out of here. And then the question is, okay, at what level do we define a threshold that says that's on as opposed to off, right? And so you can do that using machine learning. In some cases, that might give you better classification. In other cases, it might be enough just to have a training period where you're imagining, okay, now imagine your right hand, now imagine your left hand. Just record those signals and figure out what, just simple math like difference between left and right movements, and define your thresholds based on that. And formally, like as you get into this, so you've got these algorithms that are trying to make these characterizations. The question becomes, how accurately can we make them, right? Because again, these signals are noisy. And so we're never going to get 100% accuracy. Maybe someday. Nobody has achieved that yet. And so, you can be sitting there and, Flappy Bird's a bad example because Flappy Bird would be absolutely frustrating. Like it's a horrible, frustrating game to play with your thumbs, right? Let alone with your brainwaves where the decoding is not that accurate. So some 20% of the time I'm imagining a right hand movement, but it thinks I'm imagining a left hand movement, right? So the issue is, can we come up with support vector machines or some other classifier that gives us somewhat more reliable characterization?
One thing I would add to that is EEG is actually a very limited device in a lot of respects. So Aaron kind of got at that when he was talking about how it has to pass through the skull, right? And as a result, you have quite a bit of noise, especially around the spatial dimensions. One of the things is that most of the time when we're doing classification, we're really trying to decode a signal that we already know. So a live question is, are there more sophisticated signals than what we can currently see? Now, it could very well be, but a lot of times those types of projects end in disaster. Why do you think that might be? Data science people, any idea? One of the big challenges is that even if you have the most sophisticated machine learning tools, they're only going to be as good as the signal. So if the signal is fundamentally limited in the first place, it will be very hard to overcome that. So one of the things that we're hoping will happen here is people who are neuroscience expertise, people who have done a little bit of neuroscience, will know a little bit more about what are actually not necessarily loud EEG signals, but psychologically interesting things to ask. Whereas the computer science people in the room will know a lot more about the algorithms that you can deploy.